Assalamu alaikum dear students. Today our lecture is about hazardous compounds in geo-environment and concept of modeling. So basically these are two things and we will try to link them. Earlier we studied about the mechanism of contamination in soil and in groundwater. We also try to understand what is the mechanism the contaminant is moving from one place to other. We also try to understand the mechanism how a contaminant is retained within the soil. Now today we will be focusing on a very different category of hazardous compounds. So this category is actually having a different behavior other than the compounds which we used to deal with, and we will also focus on their mechanism of settlement in the groundwaters and in the soil as well. So what kind of hazardous compounds we are going to focus? So today we will be focusing on that compounds, hazardous compounds. Those compounds are called NAPLs, non-aqueous phase liquids. So these are the compounds, these are actually the liquids, but these are not as efficient or having the same properties as that of water. So they distinguish themselves from water. So these are immiscible compounds, these are immiscible liquids. These are not going to mix up with the water. So they sustain their identity. That means once these compounds are present in soil and in water, in groundwater, they will be having different characteristics to exhibit. Now those characteristics mainly relate to their viscosity, their density, their vapor pressure, their temperature. So all these things are different. While we'll talk about temperature, it is about the boiling point. So these characteristics are different from water. So they are not going to mix and deal with the same pattern as that of water. So Naples, non-aqueous phase liquids or organic liquids that do not mix freely with water. So not soluble, but in some cases some part may get dissolved in water because of some changed conditions. So if we improvise some kinds of characteristics to the system, like increased pressures or increased temperatures or reduced volumes or some kind of this activity, it will lead to some kind of mixing, but not 100% mixing. So they will sustain their identity, they will continue their identity. So the most common contaminants in these issues will be normally related to the polychlorinated biphenyls. So this is the category of compounds which are having a persistence in their nature. They will not be easily degradable under any conditions. They will sustain inert, and that's why traveling larger distances in the subsurface. So also it's not easy to distinguish them and separate them from groundwater aquifers. So that's why it is difficult to apply any kind of remedial technique to the groundwaters. So as in our discourse, contaminated site assessments and remedial techniques, in the first phase we need to focus on the assessment, on determining what is the scope of the contamination, what is the concentration, what is the impact, and how far it has gone, what kind of natural characteristics are already present in the soil and groundwater which are having their impact on the infiltrated contaminants. So the contaminant which is infiltrating will definitely modify itself based on the local characteristics of their soil volume and the groundwater aquifers. So after all kind of these kinds of investigations and determining the behaviors, how much contaminant or solute is present in the pores, how much solute has got absorbed with the soil, and how much is going to continue its movement towards groundwaters. So all these things need to be investigated. These are the major part. And when we use some software or model, or when we develop a conceptual model for groundwaters, we need to have sufficient data about these characteristics of the soil study area site characterization. And very important parameter is the sorption behavior, because when we if you remember, we earlier talked about three modes of transport, that's advection, diffusion, and dispersion. So all those have some limitations. So when we talk about advection, it is the flow with the groundwaters. When we talk about diffusion, it is simply the concentration gradients. When we talk about the dispersion, it is totally a mechanical behavior based on the local geological formations. But still, it is not so easy or so simple. It is actually a very complex phenomena. Most of the things are happening at the same time. When we are talking about advection, at the same time, there is some part of retardation as well going on. And at the same time, there is some kind of sorption going on. At the same time, some biochemical decay is taking place. And at the same time, there is some diffusion taking place as well along with the advection. So we need to incorporate all these phenomena while creating a realistic groundwater model or concept. So in that case, we need to properly investigate, and the best thing to get the data, how much contaminant or solute is present in the pores, and how much is present, how much has got attached or got sorbed with the solid phase. We need to find out the partitioning coefficient kd. So if you remember Piclet number, that is the key indicator by the help of which we can determine how much solute will be moving with the aqueous phase of the pores, through the pores and moving forward to groundwaters, and how much solute is going to get absorbed on the soil particles, that's the solid phase. So we need to distinguish, we need to differentiate between the solid phase and aqueous phase. So once the solute has entered the soil volume, there will be two kinds of phases dealing with: solid phase with the soil, and aqueous phase with the pore volumes. So later on we will talk about it, but this is something which is important to understand the a typical behavior, because it is not only one phenomena taking place, but it is a multi phenomena going on. So all need to be incorporated at the same time. Then once we have a better picture of the real conditions going on in the soil volumes, then on the basis of that, we can have a better interpretation, we can have a better model display, we can have a better simulation of different scenarios which can be developed. So once we are having much more information, and a more realistic information, then we can predict the movement of contaminant in the soils. And once we know the movement of contaminant into the soils, then we can better uh, plan for the remedial techniques, what kind of remedial measures we need to adopt. So that's our ultimate goal, to recommend the best and most appropriate groundwater remedy or soil decontamination method. Now we will further talk about these non-aqueous phase liquids, and the best thing is that these are not going to mix up with the waters, so they are separate and then they need to be studied separately. And furthermore, we can categorize them in two basic types, and those are the light weight Naples, non-aqueous phase liquids, which include gasolines, which are less dense than water, and at the same time, the second kind is dense non-aqueous phase liquids. So, and some of the examples are trichloroethylene, TCE, and so these are denser than water. So we are going to investigate two kinds of behaviors. Firstly, it is going to have a lighter weight than the water, so it is having lesser density. And then the second one is having the denser more higher densities than the water. So obviously, due to the specific weight which will vary, and we can have two different kinds of behaviors. So let's talk about the both these kinds, and let's see what kind of behavior they are going to have in parallel along with the water. So how water is behaving and how this contaminant is behaving, how this nipple is behaving in a typical environment, in a typical soil environment, and in a typical groundwater environment. A liquid solution that doesn't mix easily with water, many common groundwater contaminants, chlorinated solvents, petroleum products, all these are included in non-aqueous phase solutions. Um, so these are the types. It will how they will behave, it is important, we will talk about them. Chlorinated solvents, chemical compounds which contain chlorine, trichloroethylene, carbon tetrachlorides, and which is used as a fire extinguisher, refrigerants, cleaning agents. If you remember, these compounds are actually persistent organic pollutants which are going to have an inert nature. They are going to sustain. These are basically called conservative compounds, conservative solutes. These are actually going to sustain in the environment as it is. They are not going to react even in soils and even in groundwaters. No reaction is going to take place. They are going to maintain their identity. Now, what kind of behaviors we need to study in case of Naples? Let's see their properties. The distribution of Naples in the subsurface is the net result of coupled chemical as well as physical interaction between the Naples, pore waters, pore gases, and porous medium. The chemical properties of Naples, pore phase, and porous medium together with chemical equilibrium determine the partitioning of the compounds between the various phases, while the physical properties of pore fluid and porous medium determine the mobility of each phase. So if we talk about the chemical properties of Naples and their chemical equilibrium with the pore phase and the porous medium, it will help us in determining what is the partitioning coefficient and how this Naples will react. And so when in this case we are concerned with the sorption behavior, so And sorption is actually related with something absorbed or retained with the soil particles. So this will be having, if there is some chemical reaction going on, or there if there is a chemical equilibrium between the nipple and the pore phase and the porous medium, then we can properly find the partitioning, and we can determine how much nipple is going to remain in the soil. And while the physical properties of the pore fluid and porous medium, what kind of physical properties can help? It is about the density, it is about the specific gravity. All these things will important in this case, and this will decide whether the nipple is going to get sorbed, or it is going to move with the aqueous phase and move forward towards the groundwaters. So what kind of properties we are talking about? It is about specific gravity, aqueous solubility, viscosity, vapor pressures. All these are the properties which are about which are concerned with this movement. Now, existence in the subsurface, dissolution in the aqueous phase, volatilization into the gaseous phase, and Nipple phase as entrapped residual, and partition, sorption onto the solid phase are all the important mechanisms which are related with the behavior of this nipple in our soil and groundwaters. We need to investigate all these things. So existence in subsurface can lead to dissolution in the aqueous phase. So existence in subsurface can lead to the volatilization into the gaseous phase. Now this gaseous phase will be again in the pores, because the pores are having water as well as the gas or air. So existence in subsurface is, and its relation, Nipple phase as entrapped residual. This entrapped residual means it can be entrapped with the different physical phenomena or geological formations within the soil structure. And existence in subsurface uh, can be linked with the partition, which is actually sorption onto the solid phase. So if we talk about this partitioning coefficient Kd, so partitioning relates to retardation of the contaminant movement. So Kd is actually the partitioning coefficient. This Kd actually describes the degree of sorption of a particular species in the leachate or in the rock, and that is the in contact with the that a solid particle. So this is actually about sorption and partitioning. So partitioning is between the phases, two phases, which are liquid phase and the solid phase. So partitioning is actually, it will define which way the nipple is going to go, whether it is going to be in the aqueous phase in the pores, or it is going to get attached with the solid particles. So this is the picture which is again showing the same thing: air, water, solid, what kind of behavior it is going to have. And again, these nipples have a very high volatilization. They very quickly shift their phase, move to the vaporous phase, and easily volatile in nature, and easily movable into the atmosphere. So that's another important characteristics of this. So let's talk about the mechanism of migration by the dense non-aqueous phase liquids. First of all, let's revise what is DNAPL. DNAPL is actually the dense non-aqueous phase liquid. When we talk that it is dense non-aqueous phase liquid, it means that it has higher density than the water. So let's assume that in a in a solution there is a water as a solvent, and we are adding up this DNAPL. What kind of behavior it will show? It will be having higher density and higher specific gravities, so it will urgently immediately settle down into the bottom of the solution and of the container. This is a typical behavior which will be taking place. Now let's apply the same behavior in soils, in vadose zone, and in the saturated zone, groundwater zone. So in vadose zone, nipple plume move downward by gravity force. This is the most commonly observed behavior of this nipple. Now this nipple, if it is having volatilized DNAPL, it will move more laterally, because being volatilized, it will uh, be finding out the voids which are empty, and it will try to fill them with the vapors, and it has to move lateral. Lateral actually means horizontal movement. So this lateral movement is more likely to take place in case of volatilized DNAPLs. And what normal behavior is going to be observed, it will move downward with the gravity force, because it has a higher density, it has more, uh, so it will not sustain in the ports, but it will move forward. In the saturated zone, what kind of behavior it will be showing? Moving rate is slow due to the resistance of water displacing water, and some chemicals will dissolve in the flowing groundwater, forming contaminant plume, and the remainder will move downward, create the residual nipple zone. Mobile DNAPL will reach to the impervious layer, spreading laterally as liquid pool. Now let's see all this in a pictorial demonstration. Here you can see that this is the solvent, and we have some leaky tank gas here, and there is spillage. And just observe that in above the groundwater there is a smooth flow downwards, but at the same time we can see some volatilization, but due to the impact of its higher density, the contaminant is settling down to the bottom of the aquifer, which is having a impervious layer. So then all the Napal DNAPL, which is dense, it is going to settle down into the bottom, and it will be having it will be making a liquid pool in the bottom. So there and at the same time the groundwater flow is in moving some of the plume, some of the DNAPL will get dissolved with this groundwater and mix with it, and it will move with the groundwater, forming a plume, TCE plume. But majority will be settling down in and forming a liquid pool. What normal case can take place if it is a non-Nipple case, which is non-aqueous phase liquid? The contaminant is having the same density as that of water. So you will see that majority of the contaminant will get dissolved in water, and it will move along with the water, forming the plume, and there is no settlement in the bottom of the impervious layer. Now mechanisms of migration by light nipples. So light nipples have lesser density than the waters. How it is going to behave? So in vadose zone it will behave similarly as that of the water, as that of the dense non-aqueous phase liquid, and it will not be different from this light nipple So how it will take place? It will simply settle down along with the gravity, and at the same time in saturated zone spreads out laterally by the gravity, forming a pancake or lens on top of water table. Because the density is less, it will not have a settling force, and it will try to float on the surface of the groundwater. So the majority of the light nipples will float on the surface of groundwater laterally. So lateral movement can be observed in the groundwater as well. While in the previous case you observed that majority was settling down into the bottom and where there was an impervious layer. So this is the difference between the two. And this is the demonstration, pictorial demonstration, in which you can see a pool or lens formed at the top of the groundwater level, water table level, and some of the contaminant, some of the nipples are moving along with the groundwater flow. So now you can see the immigration patterns for Nepal. There are three immigration patterns, and which include vapor phase transport. The vapors has their own path. They move along with the air, and wherever there will be some space or void empty, the volatile matter will try to occupy it, and it will come up to the surface as soon as possible, because they are immediately supposed to enter into the atmosphere. So while there is another phase which is aqueous phase transport, as solute within contaminant plume, and then the Nipple phase transport. So three kinds of behavior, three kinds of pathways, immigration pathways of Nepal do exist. So let's go through these phases. So vapor phase transport normally follows the gas law, as we talked earlier, and volatilization, vapor pressure more than this atmospheric pressure, and then semi-volatile is having this much atmospheric pressure. So and Henry constant can relate volatilization. So all these things are a migration of gas, advection, dispersion in vadose zone larger than the saturated zone. Of course, because we have more wires available in the vadose zone. And vapor extraction method can be used, because by using some uh, wells installed for the vapor collection, we can get this removed. This method can be used. So vaporization, vapor extraction method can be adopted to clean this kind of behavior, vapor transport. Now the second one is the aqueous phase transport. And in this case, the tendency of aqueous phase transport depends on the water solubility and groundwater flow. So magnitude of aqueous solubility of Naples is a few order difference, depends on the polarity, temperature, salinity, dissolved organic matters. Movement is caused by advection and dispersion, dilution in case of enough travel distance. These are the basic properties once the nipple is entering in the aqueous phase, and then it will be following these properties. So temperature will be effective, salinity already of the aqueous phase will be important, how much saline it is, and how much already dissolved organic matter is present in the aqueous phase. It is important, because if it is already saturated, it will not be having the uh, um, uh, possibility of entertaining more saturation from the nipples. And of course the dilution will take place once it is moving to the longer distances. Now the Nipple phase transport, Nipple in water flow. Now, how it will differentiate from the water. It is important in this case, in this phase. When a wetting fluid, such as water, displaces a non-wetting fluid, such as oils, in a porous medium is the pores in the vadose zone. So, a proportion of the non-wetting fluid will remain entrapped in the medium pores, and once the wetting front has passed, in general, the non-wetting fluid is trapped in the form of disconnected blobs, uh, whose complicated morphology and distribution are dependent upon the geometry of the pore space and density, contrast, viscosity ratio. So it is something about the aqueous phase, where we have two fluids. One is wetting fluid, that is water. Other one is non-wetting fluid, which is oil. So both of them will be having separate behavior. Once the wetting fluid, water, it moves forward, then the nipple will most of the cases will not mix with that water. It will have its own flow, and in most of the cases it will depend upon its type, whether dense or light. If dense, it will have more specific gravity, more density, and more faster movement towards the downward movement. But if it's lighter, it will not be easy to move unless it is compelled by the water, wetting fluid. So in that case, it will be getting trapped in the pores, and especially it will depend upon the geometry of the pores, and especially it will also depend upon the morphology of the rocks, what kind of rock behavior is there. So there will, if there is any kind of interlocking of, or if there is any intrusion of it, or if there is any provision to capture or entrap this an apple, then it will be entrapped in that location, which is a physical phenomena. So now that is actually related with the physical size and geometry of the pore, how much the apple will be entrapped. So while the wetting fluid has already moved forward. Now in this case, sorption of contaminant is important. As we talked earlier, that this sorption behavior is understood by the partitioning coefficient, and this partitioning coefficient relates to the retardation of the movement of contaminant. So this sorption, if we have some sorption phenomena taking place, it relates with the retardation factor of the movement, because movement is linked with the aqueous phase, not with the sorption behavior. So if the sorption is there, it directly links with the retardation. So this retardation factor is actually linked with the sorption behavior. More the sorption, more the retardation, lesser the movement. And so as we talked earlier, we can determine how much the content will be sorbed and how much will be dissolved in the aqueous phase. It can be done by a testing, and that testing is a batch testing. So by batch testing we can determine it. So sorption causes contaminants to move slower, so retardation factor is there. Effects of sorption should be considered both in evaluating the potential for movement of the contaminants in soil, so and also designing remediation activities at hazardous waste site are linked with the sorption behavior. Now moving forward, concept of sorption. Sorption is determined experimentally by measuring the partitioning of the contaminant onto the particular sediment, soil or rock. So this was we were earlier talking about, that Sorption can be determined, measured by the partitioning coefficient, and that partitioning coefficient will be determined by the batch test. In batch test, we have a number of solutions, like wetting solution is there, water is there, the Nipple solution is there. So we have a different behavior, and we can then check the equilibrium, chemical equilibrium. So basically what we do, we normally prepare a solution, and we thoroughly mix it, and then we mix through the centrifuge machines, and once it is thoroughly mixed, then we add another solution, another solvent in it. Again we add the known concentration of a solute in it, and then again we measure. We again mix it thoroughly through the centrifuge machines, and then again we try to relate the two different solvents with each other. So by comparing the solvents, and then uh, it is also called solvent extraction. So once we have a solvent known as water, the other solvent is another with other some density or other characteristics, so we can easily link them with both, and then we can add up solute of known concentrations in it. So by adding the known concentration, and then after the centrifuge machine about 48 hours, firstly we do it by 72 hours, and then we add more solvent, and then we mix it for 48 hours, and then we find out the concentration of their solute, how much is left in the solution, and how much has parted it. So by the difference in the concentrations, we can find out how much is how much contaminant or solute is going to be sorbed, and from this we can find out the KD value, partitioning coefficient value. Now that was all about the behavior and characteristics of the Naples. So that's a very important thing, because in our most of the contaminated sites, the main contaminant or solute is Napple. If we, the major source, as we studied earlier, of this soil contamination and groundwater contamination are the industrial waste, or the landfills, and the petroleum sites, oil drilling wells. Because and at drilling wells, most of the solutes are the um, oil related products, petroleum products. So all the products are belonging to the uh, Nepal category, and we must have a concept how to deal with this kind of um, contaminant. Now let's just have a quick look on the mechanism how to develop a conceptual model. So we should have a thorough understanding about the site characterization, and then we should have a subsurface hydrology information, like how much is the depth of the water table, and then how much deeper the groundwater aquifers do exist. Then we should also have understanding of how much water is going to enter into the system, and how much water is going to react within the system, and how much water is going to release from the system. So this is something about the processes we need to model, and this is the calculations of head and flow. We need to understand the movement of water, and the solute transport requires information on the flow velocities, because the solute is going to move along with the water. We need to calculate the concentrations at different points. We need to understand their behaviors, and then we should have these are the models. We can have a physical model which can predict, and have uh, we can have a mathematical model, and then these are some of the examples. So we need some language, computer programming languages to execute the differential equations which will be formed for the transport of the contaminant. So firstly we need equations, governing equations for water movement, groundwater flow equations, and these are again differential equations. And then when we add up the contaminant or solute in it, we again need to modify these groundwater governing equations, differential equations. So all these equations must be run through the uh, some computer language, mostly Fortran language. Other languages can also be used. And then the component of mathematical model is basically the governing equations, differential equations, boundary conditions need to be defined of the model. We need to define the initial conditions of the concentration and how the concentration is going to change with the time. It is important to know. So the governing equation of solute transport is the advection dispersion equation. We earlier talked about this advection dispersion equation in our initial lectures, 6th or 7th. Then mod flow is one of the models which is used for the determining the groundwater flow, and it is used for developing different scenarios related to groundwater flow. MT3DMS is the package for the transport, solute transport. And this MT3DMS is actually linked with the mod flow. Firstly, we will run the mod flow for the groundwater movement, and then we will using the same conditions we will run the MT3DMS, because our water scenario is not going to change. We will be using the same equations, we will using the same boundary conditions, we will use same initial conditions, and then we will be simply adding the concentration of the solute for this MT3DMS and we will run it on the same pattern as that of mod flow to determine the fate of the contaminant in a typical environment. This was something about the conceptual model, a descriptive representation of groundwater system that incorporates an interpretation of geological, hydrological, geochemical conditions, including the boundaries of the problem domain. So this is something about what kind of scenarios we will be developing. These scenarios are actually um, based on the possible conditions, like variation of temperature and variation of location, at which location we are going to conduct our study, change in the influx. So it is also possible that our influx of water may be increased due to the precipitation, rainfall, or some other source. So we must understand the changing possibilities. These possibilities are called different scenarios. For every conceptual model, we need to establish different different scenarios, conceptual scenarios, which are possible. So against each scenario, we are going to conduct a different study. So that study will be only based on the typical conditions which we earlier assumed. So this was something about the models, and I think so that's all. Still, if you have any question, please you can ask. Thank you very much for the lecture.